My name's Tom and I'm going to be talking today about the CMake build system for HELYX Core. This system was released in HELYX 3.3.1 and it offers some significant advantages over our previous system. I should point out before we begin, whenever I refer to HELYX in this talk, I'll be talking about HELYX Core, which is the open source CFD framework supplied by ENGYS, not our closed source GUI. The goal of this webinar is to introduce you to CMake, specifically our implementation of CMake, to explain why we moved to CMake and what benefits you might see, and to demonstrate how the new system works for some simple builds. So I'll start by talking about what CMake is and the benefits that we already get from it. The first question is why we should bother compiling HELYX Core at all. HELYX Core is the open source CFD framework supplied by ENGYS, and it does all the numerical heavy lifting. It's therefore very important to get all the performance we possibly can out of the code. So, for example, HELYX Core is often used to run huge numerical simulations on supercomputers, which tend to have their own very high-performance implementations of libraries like MPI. Building HELYX against these libraries can be a great way to reduce costs and run times. You may also have your own custom code that you want to use with HELYX. The need to compile HELYX Core isn't new, and before version 3.3.1, we used to use a build system called CMake. CMake is a system that HELYX inherited from the OpenFOAM project, and in essence it's quite an elderly collection of bash scripts and custom code. It was originally developed specifically for OpenFOAM and is now maintained in-house. It's not used for any other projects. The reason I mention CMake is I'll be doing some comparisons of CMake against CMake, but the focus of this talk is very firmly on CMake. So if you're not familiar with CMake, you really don't have to worry about it. So what's CMake? CMake is a build system generator developed by Kitware, who you might know from their other software, for example VTK or ParaView, and it's the de facto industry standard C++ build tool. Google use it, Facebook use it, Netflix use it. It's as ubiquitous as anything ever is in C++. The chances are, if you see a new C++ project, it will use CMake or it will supply an interface for CMake. It's worth pointing out that this fact about CMake being a meta build system, a build system generator, is going to become important later. The CMake build system for HELYX has several big advantages over CMake. The builds themselves are already slightly faster, and we have plans to make them much faster sometime in the future. We get much faster front-loaded failures, and lots of everyday jobs like no-op builds and relinking and so on are much faster, which makes the whole thing much nicer to use. We've tried quite hard to configure the CMake interface to make it easier to use in other ways as well, with most of our efforts going into a bash script called EMake, which provides a front end that will look familiar to anyone who's used CMake before. As well as being faster and easier to use, the CMake system is also more robust than CMake. We no longer rely on environment variables, which are a constant source of pain with CMake, and CMake is much better at doing things like keeping track of your dependencies and keeping them up to date, so it's much harder to accidentally break your build. Another big benefit of CMake is that we get access to all the third-party tooling that you'd expect from the industry standard tool. You can change out the front end. All of the front ends listed here will be familiar to anyone who's used CMake before. If you're doing development, you also get really good IDE integration, so as well as your build and run and debug integration, you get easy access to static analysis tools like linters and things like go-to definition, which makes writing HELYX code much easier. You can also swap out the backend, and I'll talk more about that a little later in the talk. And the list goes on. There's loads of really nice tooling out there for CMake. The most important benefit of CMake is that it has a future. The underlying CMake system will continue to be developed by Kitware. We're going to keep developing our specific implementation, and in future we'll be integrating a few extensions and expansions from other sources. This is in stark contrast to CMake, which, as I say, has been deprecated in HELYX version 3.3.1. So that's a brief overview of why we've moved to the new system. Now let's talk about how this actually works and how we achieve some of these benefits. It's worth spending a moment talking about how the CMake build system is actually defined. Everything in this slide is already implemented for HELYX. You get it for free when you get the source code, and you're not really expected to have to modify anything. So this is just some background on what's already been implemented for you. The CMake build system is defined in CMake lists files, which you'll find throughout the HELYX code. These files replace the CMake make directories and all CMake files. They contain high-level platform-independent information about the code that you want to compile with CMake. So this is immediately quite nice because there are no longer any special cases. It used to be that some binaries had special rules for compilation hidden in these all WMake files, and that's no longer the case. All of our targets are now defined in exactly the same way. The CMake lists files are reasonably self-explanatory, so I'm not going to talk too much about them. So one nice property of CMake becomes evident here. The order in which libraries and executables are built is now automatically defined. All we do is, for each binary, we tell CMake what its immediate link time dependencies are, and CMake then goes and builds a dependency tree and uses that dependency tree to ensure that everything gets built in the right order. One corollary of this is that if you know you only need, for example, block mesh and simplefoam, you can just tell CMake to go and build block mesh and simplefoam. It will then go away and traverse the dependency tree and build those libraries and all their dependencies. So you get what you want, you get what you need, and you get nothing else. So you're no longer wasting time building things you're not going to use. This also means you don't really ever have to clean your builds anymore because CMake takes care of the dependencies so reliably. Again, it just means you're wasting less time. So as well as the CMake lists files, there's some extra logic in the etc. CMake directory, but again, users really aren't expected to have to touch this. So once you've got the source code, which contains the CMake system itself, the process of building breaks down into 3 stages. First, you need a user settings file. This, as the name suggests, is where your custom settings are kept. Once you've got a user settings file, you need to configure CMake and generate a build system. So this comes back to what I was saying earlier about CMake being a build system generator rather than a build system. You have to perform this extra step in order to generate the build system that's actually used to do the build, but that process of generation is really important, and it's where we see a lot of the benefits of using CMake. So once you've done that, once you've generated your build system, you're ready to go. So one of the design principles I've tried to stick to is that there should be one, and preferably only one, obvious way of doing things. In our CMake system, all the user-facing variables are set in a single text file. This has some really nice features. It makes it much easier to pass builds around. So in WMake, for example, the build is parameterized with environment variables. This causes a whole host of problems, not least of which is that unless you're using the exact same terminal window, you can't be sure you're reproducing the same build, because you don't know which variables have been set where. Whereas in CMake, I can just send you a single text file and it parameterizes my whole build. The user settings file itself is just a text file, so you can take care of it however you like. Personally, I like to keep mine in a separate Git repository, and I use a symlink to switch between configurations. In terms of actually getting a user settings file, you have 2 options. Either you can automatically generate one from an existing WMake environment, or you can use one of the examples that we provide in the HELYX Core repository. I'll demonstrate this later, but however you do it, this generation is intended to be a one-off. So you generate your user settings file, and then you're yours to modify and look after however you like. So the configuration step does loads and loads of checks. It checks simple things like it'll check the syntax of your CMake files, right the way up to some really complex stuff, like is the version of MPI that I found the version of MPI that you're actually expecting? You can think of the configuration step as a test you do to ensure that what's in your user settings file is sensible. The 2 really important things we get from this configuration step are firstly that we get really, really fast failures, even on very complex stuff. For example, if a third-party library isn't found, you will know about it in 3 or 4 seconds, rather than 40 minutes into the build where your linker gives up because it can't find a file. The second really important thing is that you can have very high confidence that if your configuration has succeeded, your compilation will succeed as well. There are some errors that I can't find in this step. These are mostly of concern to developers. In essence, you still have to write valid C++ code. There's not much I can do about that. But I'm aiming to catch literally every other build error in the configuration step. So if it configures, it should build. So you now have everything you need. You have your user settings file, the contents of which have been tested by the configuration step. Your configuration has passed, so CMake has generated a build system, and now you just need to run a build command. The exact command you run depends on exactly which back or front end you want to use, but they all do roughly the same thing, and you can have a very high confidence that they're going to succeed. I should quickly point out that there's also a small change to the process of running Helix. With WMake, it used to be that your bash RC environment defined everything you needed to both build and run Helix. In CMake, the build environment is parameterized in the user settings file, and the user settings file is a CMake formatted text file, so it can't be read by your shell. We still need to define certain things about our environment in order to run Helix, so we need some other way to get this environment from our build system. Fortunately, CMake generates some sourceable files for us. They live in the platforms directory and they define only what Helix needs to run, as well as some little helper variables. So again, this is an improvement over WMake. There's now this really clear separation between what you need at compile time and what you need at build time. We're also not exposing all of our implementation details in your shell, and we've been able to rationalize all of our variable names. So we've removed loads and loads of duplicates, we've hidden stuff that should be hidden, and we've tried to be a lot more consistent with what things are called. This point about bash RC being deprecated is the hardest thing to convince experienced WMake users of. Bash RC and friends are completely deprecated and form no part of the CMake workflow. If you're compiling with CMake and you use any of these files, then you're doing something wrong. Please use the sourceable files generated by CMake in the platforms directory instead. So far I've talked about the general principles of what happens behind the scenes when you're building Helix, so now I will demonstrate the build process itself. The recommended way to build Helix is with the EMake bash script, so that's what I'm going to be using. More information on the fine details of how to build Helix and everything I've just talked about can be found in the Helix documentation, which is available through the ENGYS online portal. Okay, so on the left-hand side you've got my file explorer, and on the right-hand side you've got a terminal. That's where I'll be doing the compilation, just because it's nice and big and obvious. I have a clean checkout of HELYX Core and third party. The process is exactly the same however you get our source code, either through the source packs or through Git. Now, I have nothing up my sleeves here. There is no platforms directory. I've not already compiled anything in HELYX Core, that is, and I have nothing in my environment that relates to Helix apart from the path to my current working directory. You can see, by the way, all these CMake lists files, you get these for free with the source code, and like I say, there's really nothing you have to do to them. They just live there. So the first step is to get the user settings file. I'm going to use one of the user settings files that we ship in etc. CMake settings files. I would like to use the example Linux settings. If you want to automatically generate a user settings file from an existing WMake environment, please look at the documentation. There's more information in there. So the way I'm going to do this, I could copy the file and rename it. I'm going to create a new symlink. I'm going to do it in the GUI because I think that's a bit more obvious. So my symlink is going to be called usersettings.cmake, and the path is where I currently am to CMake settings files, example Linux settings. There we go. So this is the user settings file. It's reasonably self-explanatory, I think. So we start off by telling CMake about our directories. So we define our project version and our third-party version, and then for the examples, we programmatically get our Helix project dir and our Helix third-party dir. It doesn't really matter how you do this, so long as your Helix project dir and your third-party dir are set appropriately. We then get into the interesting stuff. So we tell CMake where our C compiler and our C++ compiler are. We choose single or double precision. We choose how big our labels are going to be. So that's our integer size, effectively. And then we choose our build type, which is optimized profiling or debug. We then include the advanced settings. I'm not going to talk about the advanced settings now. If you're interested, by all means, go and look at this file. And if you want to change any of the advanced settings in this file, either do it after including the advanced settings file, or go and make your own advanced settings file and remove this line, remove or edit this line. We then have our third-party settings. So all this is in the same file. In WMake it used to be kind of spread around the file system a little bit. There are basically two important things in our third-party settings. Each third-party library has these required and arch path variables. The arch path tells CMake where we expect to find the third-party library. It's normally set to point at the directory that contains the lib and include folders for that library, and the required variable. The required variable is a trinary switch. It's either on, which means CMake will immediately fail at the configuration step if that library isn't found, or it's auto, which means that CMake will compile against that library if that library is found, otherwise it will just tell you it's not been found and stop complaining, or it's off, which means we won't be using this third-party library even if it is available. There's some extra bits and pieces in here. There's a bit more detail about how you can find unusual libraries, again, more in the documentation. It's worth pointing out that these third-party platforms' long and short variables are just so I don't have to type out the entire path to all of these libraries for every instance of the arch path. So we've now got our user settings file. So the second step is now to compile third-party, because as you saw, I am relying on lots of libraries from this third-party directory. So in order to do that, I want to access EMake. So EMake lives in the bin directory. EMake. You can use EMake-H to get the EMake help. I won't go through this now. There's loads of useful information in there. The one we're interested in right now, or the two flags we're interested in right now, are the -R and the -T flags. So -R is to refresh the CMake cache. This is essentially just performing the configuration step. And -T is our third-party toggle. So if I do a bin emake -R -T, it will configure the third-party directory. There's not much interesting in here. It's quite a simple project. Everything is turned on, so if I want to compile all of third-party, I would just do emake -T all. Except I do bin emake -T all. I've already built third-party, so all of that is already there, so CMake won't rebuild it unless I go and delete some files. You will have noticed, by the way, it is slightly annoying to have to type /bin/emake. I can make this all available on the terminal in my shell, so the way I'm going to do that is I'm going to do bin emake -G. G is a flag that will generate our sourceable files in the platforms directory. So if I go into the platforms directory, we now have active build.shellrc. This is really boring. This just points to the latest build that I've done. It's an implementation detail, but it's also kind of quite useful sometimes. And then I've got my Linux 64 GCC 75 DP int 32 opt.shellrc. And this defines everything I need to run Helix. It also conveniently will put emake on the command line for me. So I can do platforms active build and now run emake -R without having to specify the full path to emake. So this is what happens when you configure Helix. This is, there's quite a lot going on here. So it starts off by telling you some obvious things that you should already know. You know, it's using this user settings file, which is actually a symlink. I'm using the Ninja build system. Ninja, for those who don't know, is a CMake backend that's developed by Google. It's developed to be a kind of fast, lightweight version of Make. It hands off a lot of the jobs that Make does to CMake, so it's actually it's a great backend to use. So I'm using Ninja, then CMake immediately does some really useful checks for us. So it checks that the C compiler and the C++ compiler that I have specified actually work. In this case, it's recognized the ABI for both of my compilers, so it's not doing all the checks that it sometimes has to do. But I know as soon as I've got to here, I've got a valid C and C++ compiler. So now we start doing the Helix specific stuff. This is all the Helix options. These are all the Helix options that you've defined in your user settings file. These are the third-party libraries, so we can see that it's found everything that we told it to find. It tells you where everything is. It also tells you that it could compile against VTK if I set the VTK arch path, but I don't particularly mind that it doesn't compile against VTK, so I'm happy to leave that there. Then get some more details about your build configuration and the source file configuration. And then Helix modules. So Helix modules are things like Helix coupled and Helix adjoint. I'm not compiling with them now. So if these modules were available in these locations, they'd be automatically compiled and nothing about this process would change. We've then got the installation and packaging step, which isn't really relevant for most users. So we know the configuration succeeded, we know it's generated a build system, so now we are ready to build. Now, as I say, there's a bunch of ways of doing this. So before I dive straight into it, I'm going to demonstrate the power of the CMake dependency tree. So let's say I want to compile just Helix solve. I can just run EMake Helix solve. And this will start churning through all of our files, compiling all of our dependencies, and it will just compile everything we need until we get the Helix solve binary at the end. By the way, this EMake Helix solve, that's equivalent to me CDing to the Helix solve directory and then running EMake. If you run EMake without any arguments, it will just build everything in the current directory and below. There's a neat thing we can do here, so I can just stop this build whenever I like and restart it, and it will start from where it left off. So you can see it compiled about 300 files, and now instead of having to compile 2,300-ish files, we only have to compile 2,000. This is really robust. I can keep doing this, and the number of jobs that we have left to do will just keep going down. So that's the dependency tree. So I can stop that and start building everything now. And in order to build everything, either I can just run EMake here, which will build everything in the current directory and below, which is everything in this case, or I can run EMake all. And there we go. We just have to wait for that to complete and we will have our whole compilation. So that's it for the live demo. It's time to start wrapping this all up. Our take-home message is really quite simple. If you want to get the best out of Helix, you should consider building it yourself. And if you're building it yourself, you should definitely be using CMake. CMake is already fast, robust, and easy to use, and it's going to get better. You can expect to see improvements from Kitware, who maintain CMake itself. ENGYS, obviously, us, will keep improving our implementation of CMake. And third-party support for CMake will also keep getting better. In terms of the benefits you'll see right now, you can expect faster builds, easier deployment, better support for your platform. And because the builds are so much more homogeneous and well-defined, it's become much easier for us to answer any questions that you have. So that brings us to the end of the talk. If you have any questions, please email us.